This is, I'm looking at integration packet number 15, problem number 6. And we're asked to look at the region R, which is bounded by the curve y equals e to the x, the y-axis, and the line 10 plus y equals 10 plus x. So quick sketch of what that curve looks like. As you know, e to the x is asymptotic to the x-axis and is an increasing function. The line 10 plus x would go through the y equals 10 and have a slope of 1, and then it talks about having the bounded other boundary is the y-axis. So we are looking at this area in here. So we're asked to use our calculator to find the point of intersection of e to the x and x plus 10. So if you take and enter into your calculator y equals e to the x and x plus 10, go ahead and graph it, and then hit, so if you graph it, hit second calc, and then number 5, which is intersection, you're going to need to change your window because the end result does not fit in the standard window. When you finish that out, you should come out with x equals 2.527963 and y is 12.527963. So again, your calculator should end up looking as what I have on the screen. I am sure you know how to find the intersection point, but just in case, a quick reminder, put in the two graphs into two functions into y1 and y2, and then hit graph so you see the visual of it, and then hit second calc's right here, intersect, which is number 5. It's going to say first curve, and it's looking for you to identify which curve you want the intersection of. We only have 2 curves in the problem, so just hit enter on first curve and second curve. They're going to ask you to guess. Just hit enter again. Feel free to put in a guess if you want, and you should have these 2 results. We're also asked in part A to store the values that we have for x into B. And so when we do that, now I had a guess in here, okay, but our value x really is 2.527962. Okay, so in order to get that into a different memory position in your calculator, what you need to do is you need to hit alpha, and then you need to hit, notice that above the store STO button there's a green X, so we need to take X, which is where your calculator has placed the value 2.5279632, and we want to tell the computer that we want that value in X to be stored in B. So we have to hit store again and hit alpha a second time. Okay, and then hit the APPS button, the apps button, because B is in there. Now, that will take the value of X and it will now be in B. So to give you a little bit of the visual again on what I did was I hit alpha and then I went down to the store button, which you can't see on this screen, but it's down in this region, left-hand corner of your calculator. And then, so I got up the X, all right, your screen would at that point just show you this X. And then you hit the store button again. So then it's going to create this arrow. And then when you hit alpha and B, B being above in the green part in the apps button, you're going to have alpha X B. And then your screen should also start saying 2.5279, etc. To confirm that you got the number into B, just hit alpha and B and you'll end up with the number. Now, having B stored into a memory slot into your calculator is very helpful for the rest of our work in this problem. So you do not have to write the entire value of X, even though this value of X with all its digits is still just an estimate. It's a lot more accurate than the estimate of just 2.5 or 2.53. In order to solve B, we need to find an integral representing the area of region R, and then evaluate the area on your calculator. Okay, we know that this point of intersection is this XY values. Okay. Now don't forget X, the X value, we have also put into B. So that's why it's saying that the integral can be set up as 0 to B. Your calculator now knows that that value is in B. So to have the area of a curve, to find the area of a curve, the area between two curves, take the integral from the lower limit, which is 0 in our case, up to the higher limit, and then the higher curve minus the lower curve. And don't forget your dx or potentially dy. Okay, so in our case, our higher curve, the one that has larger y values, is your higher curve. So that's the line, 10 minus x minus the lower curve. And the lower curve is e to the x. And don't ever forget your dx. Now you could have, because we know that in my case I put y1 as e to the x and y2 as 10 plus x, I could have also written this as the integral from 0 to b of y2 minus y1 dx. You have identified what y2, well, I have identified what y2 and y1 are, so therefore I can use that inside my integral. I can also allow my calculator to evaluate the integral using those values. To enter this integral into your calculator, you can go about it a couple of different ways. You can actually use the number value and put that in as your limit on b, or you can use the variable b. I've chosen to use the variable b up here, and that's why we actually stored it. That was the purpose of it. And I have y2 minus y1. So if your calculator is in the math print mode, you will actually see your integral as we can set it up like what I've just highlighted. If your calculator is in the classic mode, you need to use the FNINT, and I've written out what the keystrokes are over here. So you have to go to math, number 9, which is FNINT, and then vars, y vars, hit y2, because y2 is, in my case, is 10 plus x, then hit enter, and then hit a minus sign, and then vars, y1, and enter, and then we need to do a comma, it's a comma right here, x, comma, 0, comma b, and end your parentheses, and you should end up looking like this. If I've done that accurately, my value came up to 16.946967779. In part C, we're asked to set up an integral representing the volume of the solid generated by rotating r around the x-axis. It says the cross-section will look like 2 concentric circles, which in calculus are called washers. So I've drawn the graph of the 2 functions we were given, and now the idea is that we're going to take this area, okay, and I'm going to rotate that area around the x-axis. So my e to the x graph would look like a negative e to the x graph, and likewise my 10 to the x, 10 plus x is going to come down looking like that. So that's the mirror image or the reflection over the x-axis. Now that's the reflection, but we want to, inside of this revolution of this area that has been revolved around the x-axis, there's a hole in the middle. Now, the area that is solid, again, is this area down here that got rotated, but the area in green that I have here is completely empty. Now there's going to be a cross section is what it's called. It is though I am taking and I'm slicing a knife through what has been rotated. And if I was looking at those, I would have 2 circles, and the area that I'm trying to find is the area in between those 2. So if I gave you, just to draw a little bigger, this area, and I asked you to find what the area of that solid would be. I hope if we call the larger radius R1 and the smaller radius R2, well, you take the bigger circle, the area of it, minus the area of the little circle, right? So the area of the bigger one is just pi times the first bigger radius squared minus pi times the little radius squared. So how does that apply to the area that I am trying to, that I have rotated, and then trying to find the volume of what this figure would look like? Now, I can draw a little bit more of the figure for you. And if you will, it kind of looks like a, if you can really use your imagination, a horn instrument kind of opening up on on the inside. Now the outside is just a cone with even sides, just a linear line that's making up the outside. The inner side kind of looks like a trumpet, the end of a trumpet or something like that. Okay? So there is volume that we're trying to add up, and in order to create defined volume, we need to integrate area. So if we integrate area, we get volume. So where am I going to integrate from? Well, it's still 0 to b, and my bigger circle, I need to take pi times its radius, which the radius of it, of the larger circle, sorry, that's a little long. The largest radius goes from the x-axis up to the line 10 plus x. So my radius is just whatever the y value is at 10 plus x. And I need to square that. So that's my bigger circle. And then I have to subtract off the smaller circle, the inside part of these two concentric circles. So I'm still going to go from 0 to b, and instead of my radius being created by the line, it is now going to be created just to e to the x. So it's a smaller radius, as it should be. So I'm going to have pi. Put my dx in here, and then I have my e to the x squared. So then you can use your calculator to solve that problem. So as I said, you can go ahead and find what that numerical value would be for the volume as those curves were rotated around the x-axis. Or we can take a look at this a little bit algebraically and make it look a little different. If you are comfortable and it makes sense to you to show it as two different integrals being subtracted because of the concentric circles that are happening, do that. That's absolutely fine. For those of you who want to see it a little bit different way, here we go. So on this one, on this first integral, I have a pi and it's a constant, so constants can come out of integrals without any trouble. So I can do the same thing. I can pull out the pi on the second integral as well. Now if we think about just taking pi and factoring it out, from both of these integrals, I can do that as well. Okay. Now, since these integrals are have the same limits, I can actually put them into one integral. And I can say I have to take the first integral, square it, and subtract off the second integral. Now I like to put in another set of, I'll change that color so maybe it's a little better, you can see it a little better. I like to put in another set of parentheses in here, and that's because this dx is applying to both the 10 plus x squared and the e to the x. The parentheses are also really applying to the the pi's going to both of them as well. So I like to put that in. I think it's a little clearer. So in problem C, I didn't actually give you nor did I calculate the value of what that volume would be, because the question actually just asked you to set up the integral representing the volume. Likewise, it's saying the same thing in D, and you will find as we continue our work on this that that is a common question, is to set it up but not really go ahead and calculate it. On the AP exam, more than likely you will have a question that asks you to do that as well. So now on part D, it is asking us to set up the integral representing the volume of the solid generated by rotating R around the line y equals -5. Well, this question is very similar to part C, but it does have one extra piece to it. So again, we're taking this area. Now we're going to rotate it around y equals -5. So whatever my distance is here, and that distance is actually going to be a distance of 6, because e to the x crosses the y-axis at 1. So that total distance is 6, so this is going to be -11. You don't really need to be that specific on your diagram, but perhaps it'll help you. So I'm going to reflect e to the x over y equals -5, and when I reflect the 10 plus x, it will be down here. So now what's different about this? Well, the size of the circles is what is different. Our radius is now bigger than on the first one, on problem C. So this, to find out what that length is, well, whatever this function, y function value is, I can determine it by putting in whatever x value I have and then raise e to that x value. But nonetheless, that value is going to be e to the x minus -5. Now, if you think about it, may not make sense to you. You may be saying that you have to add 5 to it. Well, if I gave you this question up here, if I have a point at, it doesn't, I'll just say that its x is 1, y is 3, and again at 1, 1. What's the distance in here? Well, it's 3 minus 1 is 2. Sure you didn't have any trouble with that. Now, if I do the same thing, or have the same point at 1, 3, but I have the value, second point, at 1, -2. What's the distance in there? Well, I'm sure you can see that that distance is 5, but what did you do algebraically? You may have thought in your head, I have the distance 3, and I have another distance in the negative direction of 2, and I added those. That's correct. But mathematically, you took 3 minus -2 to get 5 as the total distance. So that's why I am indicating that the first radius, the smaller of the two radii, is e to the x minus 5. And then the larger radius being created by the 10 minus x, that radius is 10 minus x, 10 plus x, right? minus negative 5 as well. So if we put those together, and you really need to be careful about which goes first. Make sure you're doing the outer one or the higher curve, minus the lower or the inner curve. Okay, so the higher curve, so radius is 10 plus x minus negative 5. I can, of course, think about that as plus 5, and I can make that as 15 plus x. My radius squared, pi r squared, dx, I'm still going from 0 to b, minus pi, 0 to b, of my inner curve, which would be e to the x, plus 5, quantity squared, dx. Could also write it as pi, 0 to b. I like that extra set of parentheses, as I indicated before. I have a 15 plus x, quantity squared, minus e to the x plus 5, quantity squared, and that big integral, parentheses, and I have my dx.